we are aiming at this, finding the energies to be multiples of h times the frequency. And we will go step by step. Okay. So h, the Hamiltonian, is minus h bar squared over 2m d squared over dx squared plus kx squared over 2, and this was written like this. Okay. So I'm going to be heavily relying on my notes here just to make sure. So this is equation number 1. Equation number 2 is actually a definition. I'm defining something called raising operator or creation operator. So I'm going to define it like this, A plus. This is a definition, and you will see why it matters. So 1 over 2 h bar mw square root minus ip plus mwx, m omega x. This is my raising operator. And you can see a hint of this already here. So we are aiming at this kind of representation, but this will be clear in a moment. So that's the equation number 2. We also have a lowering operator or annihilation operator. And this one is defined as A minus. Same story. With a plus IP. Okay?
Can I ask you?
Sure, of course.
Why are we using three not equal signs?
Yes. This one means defined as. Okay. Very good point. Of course, always.
Why are we calling the second and third equations as rising and lowering equations?
It will be apparent very soon. It will be clear very soon. You just need to wait a little more. Okay? All right. Just hang in there. It will be all fine. So let me find A plus times A minus. Just what happens when I do that? Well, I have 1 over 2 h bar m w p squared plus m squared omega squared x squared. Okay. Is this something that I want? Let me show you that this is something that I want because it looks just like this, right? Just like this. So it starts looking like Hamiltonian. Do you see it? Yes? But we also have this term, which is a not zero, IMW over 2 h bar mw xp minus px. Ekin is proposing to put the hats everywhere, you know. Why he is proposing it at this particular moment? Because if this was just a number, then this would be 0. But these are operators, so that's why xp is not necessarily equal to px. Do you remember the matrices? And I told you, I promised you there is going to be something interesting about them. So this is that time. Let's now talk about, let this one brew on the side, okay? It's like making a dish. So this is the side dish. There's something else. You put it on the oven. While it's in the oven, you cut down tomatoes, etc. So we jump to something else. We jump to commutator. What is a commutator? So this xp minus px is written like this, and this is what we call commutator. So this could be any operation, any operator A and B. When you put it in this square brackets, it means AB minus BA. So when it is 0, we say that it commutes. A and B commutes. When it's not 0, then it does not commute. Okay? Let's actually find this commutator. So to find this commutator, I am going to operate on a function f with this commutator. So xp minus px multiplied by f. So what does it mean? It means that you have x times h bar over I del over del x minus h bar over I del over del x, x times f. So far, did you follow everything? Yes? This is a typical exam question, by the way, to derive the commutator for x and p. Okay, x times h bar over I del over del x, and f comes here, minus h bar over I del over del x, but this time it's x times f. Do you know how to deal with multiplication of two functions and taking the derivative? How do you do that? Yes. First one, the derivative of the first one times the second one plus the derivative of the second one times the first one. So you have x h bar over I del f over del x minus h bar over I. So the derivative of x is 1, so you just simply get f, right? And the other one is h bar over I x times del f over del x. What cancels here? This one cancels out that one. Do you agree? So you actually get something. You get I h bar, I just flipped I to the top, times f. Look, you started with this, okay? You end up with I h bar f. You can simply say that this is equal to that. So x p commutator is xp minus px as operators, but it turns out that those two operators, when you do xp minus px, just gives you this I h bar. Did you follow this, everyone? Yes? So is it good for us? It's good for us because, what do I call it? This is number 5. This is equation number 5. So we can use this equation number 5 in our equation number 4. This was 4. Do you see? We can put here I h bar now. Is this clear to everyone or not? Rabel? Yes? Okay. So if you do put it there, Hmm? Oh yeah. Oh yeah. Oh yeah. A plus A minus is m omega p squared plus m squared omega squared x squared plus I m omega over 2 h bar m omega. I don't know why I didn't do the cancellations, but anyways. So now I have plugged in this IH bar, right? So I've actually used it here. So what do I get? I get A plus A minus is Hamiltonian divided by H bar omega minus 1/2. That's that's very short, right? Do you see? Like this goes out, this goes out, this goes out, and you just get minus 1/2, right? And over here, how do you get Hamiltonian over H bar omega? Well, if I write H bar omega here, the rest is p squared over 2m plus m omega squared x squared over 2, right? So it is indeed Hamiltonian over H bar omega. Okay. So I can actually write Hamiltonian in terms of this raising and lowering operator, H bar omega A plus A minus plus 1/2. And this is my equation number 6. Let me remind you the promise that I made to you. I was promising you to show that E of n of harmonic oscillator is going to be H bar omega n plus 1/2. Do you see that we are very close there? Yes? Well, it seems close, but we have a few more kilometers to go. Okay. I think at this point, I got some sort of mercy and I didn't derive this. I just wrote it like this. But you can easily derive it. So it turns out that the commutator between the lowering and raising operator is 1. Okay, A minus A plus minus A plus A minus is 1. They are not commuting. It's not 0, right? It's 1. Do we call this anti-commutation, or is it when it's negative 1?
No, it's not a special name. Anti-commutation is the same with the quadratic.
Okay. It's the name for the operation, not for the what comes out. Okay. Okay. So, by the way, if you want to see why this is the case, okay, you can go, so why this is the case, you can just follow all this by starting from here with A minus A plus and see where it goes. Actually, let me tell you where it goes. Just this one flips, right? And that one was bringing you minus 1/2. So now it will bring you plus 1/2. That's it. Okay? Something plus 1/2 minus something minus 1/2 is 1. All right? So it's not that hard to show this. Okay, so what? Why did we write it at all? Let me remember. A minus A plus. Wait, I will, okay. We will use it somewhere, so let's just keep with the subject. So this is equation number 7, and equation number 8 is not that important actually. A minus A plus is h over h bar omega plus 1/2. Okay? That's what we just discussed. Now comes the part which is, I guess, the most demanding to see what's going on. So please restore your whatever. Let me drink some water. Hmm? Yes, they are operators. Very good. So we will start by let phi be eigenstate of H, which means that H phi must be E phi. Do you agree with this? Equation number 9. Okay. Then let's look at what happens. Just we are curious. What happens to A plus phi? So phi is a function. It's an eigenstate, eigenfunction of Hamiltonian. We are wondering what is A plus phi. If I just simply multiply H by A plus phi, what is going to happen? Okay? So Hamiltonian is this, right? H bar omega A plus A minus plus 1/2 A plus phi. This is what we are looking at, right? Do you have any objection to this? Did you follow this? So instead of H, I have written equation number 6. Equation number 6. Instead of Hamiltonian, I wrote equation number 6. Okay, continue. Do you agree that this is H bar omega times A plus A minus A plus plus 1/2 A plus? Did I do anything wrong here? No? Tell me. Okay. Just distributing this over here. Okay. But you know, it's a trickery. What we are doing is trickery. A plus was on the right, right? Now we are going to take A plus to the left. Look, watch what happens. H bar omega, A plus comes here, then I write it like this. People actually take home bread by doing these kinds of trickery. You know, it's a field. All right. So what? Here is what's going on. I get H bar omega A plus times Hamiltonian over H bar omega plus 1/2 plus 1/2 phi. Do you see that the equation we have used this number 8, this equation, right? Look, this one became this one. Do you see it? So what? Here's what's going on. Can I write it like this? A plus H plus H bar omega phi. Do you have any objection to this? Hmm? Are you following? Now comes the nice part. The nice part is that we know that HF is EF, right? So I can write it like this: A plus E plus H bar omega F, because HF is EF. Now it's just a number. So this one now can jump over here because they both become numbers. They were operators before. It was Hamiltonian. Hamiltonian was an operator. So when it was an operator, it couldn't jump over here, right? But we made it into a number because we are using a specific function, right? So what do I get? I basically get this: E plus H bar omega A plus phi. Now what does it tell you? Let's remember where we started from. We started from this. Can you make a comment on this? What does it mean?
A plus phi is just another eigenfunction because I gave it a root E plus H omega.
Yes. Can anyone else who haven't seen quantum mechanics 7 times? Do you see what's going on here? So it's yet another equation that has h times some function f equals eigenvalue times f. So in this case, that function is this, that eigenvalue is this. Did you follow this? So this brings us to this ladder stuff. Let me just write down what just happened. This tells us that if phi is eigenstate with energy E, then A plus phi is eigenstate with energy. You complete the sentence?
E plus H omega.
Yes. Okay. So
So this is the reason why it's called rising.
yes, exactly.
Hocam kediyi de kesek mi?
That- That would be copyright infringement, right? So I'm just plotting a ladder. It may actually become a bit more smarter and duplicate this one. Does looks like a ladder. This one should be a bit lower, right? Well, what does it tell you? It tells you that you have an eigenfunction at energy E. You go to A plus phi and you get energy E plus H bar omega. Okay? You do another A plus squared phi and you get 2H bar omega, right? And you can show that, and we are not showing it. You can go down as well, similar fashion, to E to the E minus H bar omega, and you can also go down twice if you are high enough. Okay? So you have these energy levels just like Planck devised back in the 1900s. And that's why these A plus and A minus are called ladder operators. So together they are called ladder operators. Can go up or down in that ladder. Do you have any questions at this point?
Can we go infinitely many times down?
Yeah, that's the next line. Do you have any questions? Any questions at all? Yes.
So, we understand why it's called raising and lowering, but why creation and ending?
Why?
Why creation operator?
Okay, very good question. Why creation operator? Because this is just the beginning of quantum mechanics, okay? You keep developing quantum mechanics, and at some point you start looking at it. It's called second quantization. You start looking at it not as a wave function going back and forth, but as fields, and on top of those fields you have particles emerging, coming into existence and going out of the existence, and you can define that process with these operators. Okay, worst explanation ever. So, right? Let me give you. Hmm?
Give the explanation of cavity. Like you just add one quantum energy to a cavity, so you actually create a photon inside this cavity. So it goes like that, and goes like that. You absorb that photon, so you annihilate those photons inside the cavity. So it's annihilation of this operation that you do with the measurement device that you call annihilation.
Let me come back to this subject one more time. But they are everywhere. Just open random physics paper, and you have this A plus, A minus everywhere. So this is an advanced way of looking at systems.
What's the origin of definition? What's the origin of this function?
I presume that it was originally devised to solve harmonic oscillator, okay, and then physicists already knew that everything is harmonic oscillator basically, okay, so they kept using it in other systems. Let me finish with this derivation, because I'm not explaining myself well right now. I don't like my teaching right now, but because maybe we are not finished. So, have you seen any wave function here? Do you remember sines, cosines in particle in a box? Where are the wave functions? We have already gotten the energies, but we have no wave functions to show for, right? What are these phi's? Well, let's look. So this ladder, can it go on forever? No, it can't, because one way of looking at it is this. So we started with this potential, right? And maybe your ladder is somewhere here, and at some point you are going to hit the bottom of the well, and you can't go down. Your energy can't be below the minimum of the potential energy. Why is that? Can you have any ideas? There's no negative energy, yes. Imaginary frequencies, both of them are the same stuff. It's like you have, let's think classically, you have a well, and you are asking where is the particle, and you are saying that it's below the well. That's not possible, right? in terms of energy. Like you define the zero of energy to be at the bottom, so you can't have negative energy.
But there will be always valve, right?
Say it again, please.
Will there be always valve? I mean, this shape. Can it go like this?
Yes, it can go like that. Very good question. So it can be like this. Okay. Then you can't be here. Okay. You can be temporarily there in the case when you, let's say you have a well here and a barrier and a well here. Okay. This energy is possible because it's still above the bottom of the whole thing. Okay. So what will happen is the particle will oscillate here, it will decay here, it will have decaying function there, and it will oscillate here again. But in the places where potential energy is above the energy of the particle doesn't oscillate, it just decays. Okay? Exactly. Yes. We will come to tunneling. Not now. All right. Yes?
So when the line is above 1 and below 1,
Yeah.
it's not possible?
This one is possible.
You know, when it is below the first?
Okay. Okay, that's a good question. Can this happen?
Yeah.
What do you think? Yes, it can happen. What's going to happen is that you will have an oscillating wave function here, but it will be decaying all the way here. Okay, very good question. But not below that bottom part. So, somewhere this lowering operator has to come to an end, right? And let's call that bottom level phi 0. Let's call this phi 0. So you have phi 1, phi 2, phi 3, etc. So it tells you that if you lower phi 0, you get 0. Okay, that's the only way to come out of this problem. So let's figure out what it means. Okay, let's call this number 13. So how many have we skipped? Last time we were at 9. Let me just put some numbers to the equations. I called this one number 10. This one is number 11. And also 12. Okay. All right. So let me remind you, H phi 0 must be E0 phi 0, right? So let me write it down, H bar omega A plus A minus plus 1/2. Do you remember this? Very good. Now we can couple it with number 13. Do you see that what will happen with number 13? The thing is that, okay, let me write it clearly. A plus A minus phi 0 plus H bar omega over 2 phi 0 equals E0 phi 0. Do you see what this is? This is 0, which tells you that E0 is H bar omega over 2. Not yet. Okay. So the bottom level apparently is H bar omega over 2. And we have seen that every time you go up, you go to 3 by H bar over omega. So this tells you that E of n is going to be n plus 1/2 h bar omega. That's what I promised you. This is where we circle back to how it started, with harmonic oscillators not being able to have any energy they want. Do you remember? Now we can show it. Now we can say why, and our why is starting from Schrödinger's equation. This is how nature works. It obeys Schrödinger's equation, and it prohibits us to have any energy that we want. We have to have these energies. As you questioned, what about the ground state wave function? So for the ground state wave function, we can remember the definition of A minus itself. I don't know if you still remember it, but it was this. Do you remember it? So it had h d over dx m omega x by 0 is 0. Right? So d over dx phi 0 is equal to minus m omega over h bar x phi 0. Then you have d phi 0 over phi 0. The nice thing is that at the beginning, when we had this mathematical preliminary, we are still using those things and nothing else. Okay? Although it seems like we are going too deep into mathematics, but we are really using the same stuff over and over again. And for this one, we are, when you integrate this, you are going to get phi 0 constant times e to the minus mw over 2 h bar x squared. So it's a Gaussian. Do you see? It's some sort of Gaussian. And how do you find normalization constant? What do you think? Any ideas for how we find normalization constant? Yeah. Normalization. The integral of the square, so the integral of phi 0 squared dx must be 1. That's how you find A. Okay? What time is it? Okay, we have 10 more minutes. What we have left out is the discussion of raising and lowering operators, right? Do you have any questions? No? Yeah.
I'm wondering that the pi 0 or its variance are correlated with the SPDF energy level. We say that as we continue with the
SPD, you mean atomic energy levels? Very good question. So we have seen particle in a box, right? In a box. We have seen the box, basically. Box, particle in a box, particle in harmonic oscillator potential. And what you are asking is hydrogen atom. So for this one, V was 0, right? It was a box and we got these energy levels. For this one, V was kx squared over 2, and we got ourselves, okay, let me draw it properly, this, right? For this one, we are going to have this potential, right? It's electron and proton. What? Circulating. And notice that this one we did in 1 dimensions. This one was also in 1 dimensions. This one is in 3 dimensions. So we need to move to 3 dimensions. And in this 1 dimension, we got 1 quantum number. So it's like h bar squared pi squared over 2ma squared. Then there is a quantum number, n squared, right? Over here, it's h bar omega n plus 1/2. There's again 1 quantum number, right? For 3 dimensions, you are going to have 3 quantum numbers, n, l, and m. Okay? That's what is going to be like when you have 2p6 kind of stuff. Let me just 2p orbital being like this. Okay? N will correspond to this, L will correspond to this, and M will correspond to where you are in that box. Okay? Does it make sense?
Isn't there actually 2 in Harmonic Oscillator?
No. Why? There's only 1 quantum number. It's 1-dimensional potential. No, don't think about polarization. Then you complicate things. Okay. I'm trying to formulate the answer to your question, but you caught me off guard, to be honest. So let me answer your question next lecture. Your question is important. Like raising up, why do we call it creation and annihilation? Okay? So let me formulate my answer and come back to you with that. Any other questions?
So, could we say that in the harmonic oscillation, when we step forward from one phi value to another, could we say that a particle begins to oscillate faster? It's changed its frequency. I'm trying to understand what's the meaning of the difference between this phi energies.
Okay. We still have time, I guess. Let me see if I have the... Let me see what I have here. Okay. Unfortunately, I don't have harmonic oscillator with me today. As a code. Let's, for your question, let me bring my harmonic oscillator code, and we can then play with that one. But what is your question again? The question is,
What's changed in the particle between the different phis?
different phis. So what does it mean to be at this level and at that level?
Yes.
So at this level and at this level. Okay. What does it mean to be over here, over here, over here, right? It's not that different from particle in a box. We have seen that the ground state is rotating slower. The first excited state rotates faster. So as the energy grows, it rotates faster, but it doesn't mean oscillation. It doesn't mean oscillation. It doesn't go back and forth. To get the back and forth, you need to use combination of 2 levels, like phi 1 and phi 2. When you put them together, then it oscillates at a certain frequency. I don't know if it makes sense or not. I see. I see. I see. You want to reconcile classical harmonic oscillator with quantum harmonic oscillator, right? What happens there? So the answer is classical harmonic oscillator can just sit still, right, and do nothing. Quantum harmonic oscillator can't do that. It has to have some kinetic energy. Okay, that's h bar omega over 2. And then it wouldn't accept just any energy. It has to accept only h bar omega. So if you have a quantum harmonic oscillator, it can shine light that is a multiple of omega. Like only those frequencies of the harmonic oscillator, and its multiples can come out as emission or as absorption. It can take in only those frequencies. Okay, back to Planck's model. If you include this in Planck's model, right, everything is explained, because Planck thought of it as harmonic oscillators, and the oscillators that are abundant with higher frequencies would require higher energy to get excited. And since that higher energy doesn't come together at certain temperature, they wouldn't get excited. So that's the whole story. Any other questions? Thank you very much. Let's stop here.